Periodicity 2, Trends in Physical Properties. The essential idea is that elements show trends in their physical and chemical properties across periods and down groups. Nature science is looking at patterns, or looking for patterns. The position of an element in the periodic table allows scientists to make accurate predictions of its physical and chemical properties. This gives scientists the ability to synthesize new substances based on the expected reactivity of elements. Understandings we get are that vertical and horizontal trends in the periodic table exist for atomic radius, ionic radius, ionization energy, electron affinity, and electronegativity. We also find trends in metallic and non-metallic behavior due to the trends above. Application skills. Prediction and explanation of the metallic and non-metallic behavior of an element based on its position in the periodic table, and discussions of the similarities and differences in the properties of elements in the same group, with reference to alkali metals, which is group 1, and the halogens in group 17. Properties of elements repeat in certain patterns when you move along the periodic table, and we call this periodicity. You can see in this graph here, it shows the trends in ionization energy for atoms, and we've got atomic number along the bottom of the graph, and we've got ionization energy on the y-axis. Here we have helium, and you can see helium has a very high ionization energy, and it drops as you go into the next row, with lithium having very low ionization energy. Then, as you go along the second row, you can see that the ionization energy steadily increases until you get to neon. Then it drops again when you go to sodium at the beginning of the third row, and it increases again till you get to argon here. So if we just look at going down a group, we're going to look at those noble gases. You've got helium, neon, argon. There's a gradual decrease in ionization energy. And if we go across the row, if we go from lithium to neon, you can see a gradual increase. And if we go from sodium to argon, you can see here a gradual increase. Many properties of elements can be explained based on the strength of the force of attraction between the nucleus here and the outermost electrons, the valence electrons. Okay? And it's the attraction of those valence electrons to the positive protons in the nucleus that determine these properties. Some factors that affect the force of attraction include the number of energy levels. Here we have one energy level. Over here we've got 3 energy levels, and the valence electron is in the 3rd energy level. With fewer energy levels, you get a stronger force of attraction between the positive nucleus and the outer electrons, as you would imagine. And with more energy levels, you get a weaker force of attraction because the positive nucleus between the positive nucleus and the outer electrons. The strength of the force of attraction varies inversely with distance. So the further away you get, the weaker the force of attraction. Another factor that affects force of attraction is nuclear charge. So if you've got the same number of energy levels, let's say we're going along the 3rd row here, from sodium across to chlorine. The one valence electron in sodium is attracted to a charge of 11+, and the valence electrons in chlorine here are attracted to a charge of 17+. So a lower nuclear charge gives a weaker force of attraction between the positive nucleus and the negative outer electrons. A greater nuclear charge gives a stronger force of attraction between the positive nucleus and the negative outer electrons. The strength of the force of attraction varies directly with nuclear charge. As nuclear charge increases, force of attraction increases. Another factor affecting force of attraction is the inner shielding effect. When we go down a group, the nuclear charge increases. And it's not important for some reason. Why is it not important? You can see here that there are 10 electrons between this outer valence electron and the nucleus here. Over here, there's no inner electrons between the nucleus and the outer electrons. The force of attraction is stronger than here, where the 10 inner electrons and the first and second energy levels shield the outer electrons from the interacting forces of the nucleus. This reduces the strength of the force of attraction. Another factor affecting the force of attraction is effective nuclear charge down a group. Effective nuclear charge is the charge remaining after the effect of inner shielding. Okay, so the effective nuclear charge is basically the nuclear charge minus the number of inner electrons. So here, this example, we've got 2 electrons shielding the outer electron, and over here we've got 10 electrons shielding the outer electrons. The effective nuclear charge for this first one is going to be +1 because you've got a charge of 1 and no shielding. Over here we're going to get a charge of 3, because it'll be 3 protons, and you've got 2 electrons in that first shell which is shielding this electron. So 3 minus 2, you get a charge of 1. Finally, over here, you've got a charge of 11, because you've got 11 protons here, and you've got 10 electrons shielding this valence electron. So you're going to get effective nuclear charge of 1. The effective nuclear charge is the same for all elements in a group. Okay, the inner shielding effect increases. This here, the center one, there's more shielding going on here, where there's essentially no shielding, but less so than over here. And here we have a lot of shielding going on. The effective nuclear charge across a period is a little bit different. So, the charge remaining after the effect of inner shielding, and we're going to get the same amount of shielding, aren't we, across the period, because you're always going to have, you're just adding electrons to the outer energy level. So here you're always going to have 10 electron shielding. Okay, so for sodium you have 10 electron shielding. For aluminium you'd also have 10 electron shielding, and indeed for chlorine you're still going to have these 10 electron shielding. So let's do the math. We've got a charge of 11, we've got 11 protons. Take away the 10 shielding electrons, we've got an effective nuclear charge of 1. Here, 13 protons with 10 electrons shielding. 13 minus 10, that's going to give us an effective nuclear charge of 3. And over here we have an effective nuclear charge of 7, because we've got 17 protons and 10 shielding electrons. So the effective nuclear charge increases going across the row. The inner shielding effect is the same. Let's have a look at trends in atomic radius. 1 picometer is 10 to the minus 12 meters. You can see a big jump in atomic radius as you go from helium to lithium. Obviously you're adding another energy shell, or another energy level there. Then you get a gradual decrease in atomic radius as you go from sodium along the road to argon. Okay, and then you see the atomic radius increasing quite dramatically as you move to the next period, and we've got sodium there, and then another gradual decrease as we go from sodium down to argon, and then another leap back up as we start another row. So there's a very gradual increase here if we just look at lithium to sodium to potassium. So you get an increase in atomic radius as you go down a group. And then if we go from lithium to neon and sodium to argon, you can see a gradual decrease. So across a row, the atomic radius decreases. As we go down a group, we explain the atomic radius increase because of the number of energy levels. The energy levels increase as you go down a group. The distance between the nucleus and the outer energy level increases, and so you get a weaker force of attraction. As we go across the road, we explain the decrease in atomic radius because it has the same number of energy levels, but the nuclear charge is increasing, so the strength of force of attraction between the nucleus and the outer electrons increases, which pulls the outer energy level in closer. Trend in atomic radius. Cation radius versus atomic radius. You can find these in table 9 of the data booklet. If we look at sodium here and the sodium cation, you can see there's quite a difference in size. Okay, the atom is a lot larger. You can see the big difference is, of course, that the sodium atom has a third energy level, whereas the sodium ion just has 2 energy levels. The cations have a smaller radius because they have lost one of these energy levels. And there's also a higher effective nuclear charge of +9, and there's less inner shielding for the cation. Conversely, if we look at anions compared to atomic radius, we'll use chlorine. You can see that the anion is larger than the atom, again by quite a bit. Let's put those electrons in. Okay, the anions have a larger radius because there is electron-electron repulsion. When an extra electron here is added to the outer shell, you get electron repulsion, and the overall ion has a negative charge, obviously. You'll notice that the number of energy levels is the same in both, and the effective nuclear charge, if you did the maths, is the same, and the inner shielding effect is the same. So when explaining this, you explain solely by this electron-electron repulsion that's occurring, which makes the ion larger. Okay, see if you can rank these elements in order of decreasing atomic radius. First of all, bromine and potassium are the only 2 elements here that are from the 4th period. So they've got 4 energy levels, so they'll be the biggest. Potassium has a smaller nuclear charge than bromine. So the electrons in the outer, the valence electrons of bromine will be drawn in more strongly towards the higher nuclear charge of its nucleus. Next, we'll go to the 3rd period, and we have magnesium, which has the smaller nuclear charge, followed by silicon, followed by chlorine with the greatest number of protons, but the magnesium, the silicon and the chlorine all have the same shielding effect, and the valence electrons are in the same energy level. So let's rank these particles in number 2 in order of increasing radius. In this, we have some cations and some anions. Let's just write down how many protons and electrons they each have. That'll be very helpful. Straight away you can see that, let's have a think, magnesium here still has one electron in the third energy level. So it will definitely be the largest. All the others have 10 electrons. So this, and this all have the same number of electrons, okay? So the same shielding. So the thing that will determine their size will be the nuclear charge. And so we can take a look. You can see the magnesium has the greatest nuclear charge, so it will attract those outer valence electrons with the greatest strength, and so it'll be the smallest. Then we can just follow along to sodium, fluorine, and then oxygen. Sodium, fluorine, and oxygen. Okay, let's look at the trends in first ionization energy. We go from hydrogen up to helium, and there's a big jump straight away, and then a catastrophic fall back down to lithium, a gradual rise as we go along to neon, and another fall as we go to sodium, and then as we go along that third period, it reaches up to argon, and then it drops down again. So we can see as you go down groups, the ionization energy decreases overall. You can see a gradual decrease here in the noble gases, and over here you can see it too as you go from lithium to potassium. As we go up a group, as we go along a period, the ionization energy does increase. It increases across a row or across a period. And again, that's overall. You can see there's stuff going on here. So, but the general trend is an increase. The first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of an element. The explanation for this. Down a group, we explain the decrease in ionization energy as because the number of energy levels increases as you go down a group. The distance between the nucleus and the outer electrons increases. So the force of attraction between nucleus and outer electron decreases. And so less energy is required to remove the outer electron, which makes sense. As we go across a row or a period, the ionization energy increases. So all of the atoms have the same number of energy levels, but the nuclear charge is increasing. The force of attraction between the nucleus and the outer electron increases, so more energy is required to remove the outer electron. Okay, let's have a go at this question. Rank these elements in order of decreasing first ionization energy. First pause and have a go. Okay. Well, first of all, we have beryllium there, which is the second element in the second period. And it only has 2 energy levels. Calcium, on the other hand, is in the 4th period, so it has 4 energy levels. Magnesium, sodium, and silicon have 3 energy levels. So beryllium, only having 2 energy levels, will have the highest ionization energy because more energy will be required to remove those electrons that are closer to its nucleus. Calcium will have the lowest because it's easiest to remove those electrons which are further away from the positive protons in its nucleus. Magnesium, sodium, and silicon all have 3 energy levels. And so what will differentiate their ionization energies, or the ease of which they can lose electrons, will be the nuclear charge. And silicon has the greatest nuclear charge of the 3, followed by magnesium, followed by sodium. And so we should see that silicon will have the highest ionization energy, followed by magnesium, followed by sodium. Okay, this is a bit of a review. We're going to look at the exceptions to the increasing trends across a period. We've got beryllium dropping down there to boron. We'll stick all these others in. And you can see we've got magnesium, and there's a drop in ionization energy as you go along to aluminium. If you recall, this was evidence for sub-levels for these two. We'll talk about that later. Okay. If you consider the energy values for the sub-levels within an energy level, we know that S is smaller than P, which is smaller than D, which is smaller than F. So here, the P sub-level here has slightly more energy and slightly further away from the nucleus than the S sub-level here. Okay, so it's easier to lose this electron, requires less energy than it is to lose this one, because you're just removing the first P orbital here. For the explanation for this drop in ionization energy for nitrogen to oxygen or phosphorus to sulfur, this is explained and is evidence for Hund's rule. It's how we found Hund's rule. If you consider filling the orbitals in a sublevel for nitrogen compared to oxygen, for example, you've got 3 electrons, each unpaired, whereas here you have a pairing of electrons. In oxygen and sulfur, the pairing of electrons in the p orbital causes electron-electron repulsion, and it reduces the energy needed to remove the first p orbital. So these here, it's easy to remove this because there's slight repulsion between these two, and so less energy is required to remove this electron compared to the first one here, which is unpaired. Okay, trends in electronegativity. You can see a decrease as you go from lithium to sodium to potassium, or as you go from fluorine to chlorine there. So going down a group, you get a slight decrease. However, as you move along a period or across a row, you can see the electronegativity increases. We explain this. First, let's remind ourselves of the definition of electronegativity. It's the relative measurement of the ability of an atom to attract a shared pair of electrons in a covalent bond. It's measured using the Pauling scale, which is 0 to 4. The explanation for electronegativity decreasing down a group is that the number of energy levels increases. So the distance between the nucleus and outer electrons increases. So the force of attraction between the nucleus and outer electron decreases. Across the row, we explain the increase in electronegativity because the same number of energy levels exist, but nuclear charge increases. The force of attraction between the nucleus and the outer electrons increases. Okay, moved on a bit quick there. Just another look at that. Right, trends in melting points. Melting point trends going down group 1. The structure and bonding of group 1 elements is as follows. You've got free electrons from outer shells of the metal atoms who can move freely between the metal ions. Remember, that's metallic bonding. So the effect on melting point as you go down a group is that to melt metals, you've got to break those metallic bonds. The metallic bond strength depends on 2 things: the ion charge and the ion size. If we just think about group 1, obviously the charge stays the same. It's always +1, but the ion size does increase, and so the metallic bond strength decreases as that size increases. So the melting point also decreases. Let's have a look at the melting point down group 17. We've got fluorine, chlorine, bromine and iodine. They're non-polar molecular covalent substances, and the molecules are held together by dispersion forces. To melt halogens, you've got to break these dispersion forces. The strength of dispersion forces depends on the total number of electrons, and as we go down group 17, the total number of electrons increases as you go from fluorine to chlorine to bromine. So the strength of dispersion forces increases, and therefore the melting point increases. Okay, let's look at the trends in melting points across period 3. For the first 3, sodium to aluminium, from here to there, the ion charge increases. Sodium plus 1, then you've got magnesium plus 2, and then aluminium plus 3. So the metal bond strength increases. Therefore the melting point increases. Then we've got silicon, which is a giant covalent solid. It's got covalent bonds throughout, and these need to be broken during melting, and so it has the highest melting point because of those strong covalent bonds. Then we have phosphorus, sulfur, chlorine and argon here, and they're non-polar molecular covalent solids or atoms. And the weak dispersion forces are very easily broken, and you get a general decrease as you move along them. Okay, let's see if you can answer these questions. Press pause and have a go. Right, which substances are made of molecules? So we know that oxygen and bromine are made of molecules. Oops. What force bond is broken when the substance in question 1 melts? If the dispersion forces, the covalent bonds between the atoms aren't breaking, it is only the dispersion forces between the molecules. Next, in which substance, I keep pressing that first, in which substance are covalent bonds broken during melting? In silicon, you have the covalent bonds throughout, it's giant molecular structure, and so it's the covalent bonds that need to be broken. That's why it has such a high melting point. And let's list the substances in order of decreasing melting point. Silicon has the highest, it being a giant covalent. Then you've got the metal, potassium, you've got the 2 diatomic molecules, which have more electrons, so they've got dispersion forces, and then you've got argon as the lowest. Trend in electron affinity. In the chlorine atom here, you've got nuclear charge 17 protons, and you've got valence electron, no sorry, it's not a valence electron, an outer electron, which at the moment isn't involved in the atom. That's important. It's not a valence electron in this picture. Electron affinity is a measure of the attraction between the incoming electron and the nucleus. The stronger the attraction, the more energy is released. The factors that influence the electron affinity are the same as those for ionization energy. It's just nuclear charge, it's distance, and it is shielding. The definition of electron affinity is the energy change that occurs when 1 mole of electrons is added to a mole of gaseous atoms. So it's electrons coming from another source. Let's look at trends in electron affinity of the halogens and alkali metals. The general trend for halogens is, as you can see, they generally go down the group. The electron affinity values decrease. There's less energy is released when the anion forms. The exception is fluorine. This is due to its very small size. Its electron density is high, and so the extra electron is put into a region of space with high repulsion. This repulsion reduces the attraction of the incoming electron, the incoming electron field, and so the electron affinity decreases slightly. Group 1, the alkali metals. Again, a general trend. As you go down the groups, the electron affinity values decrease. Less energy is released when cations forms. Do note that we don't usually discuss electron affinity of metals, as they tend to lose electrons, ionize, rather than gain electrons. Thus, the electron affinity values of metals are much smaller than those of non-metals. Okay, let's look at trends in metallic versus non-metallic character. Metals, what properties do they have? Well, they're good conductors of electricity and heat. They're malleable and ductile. They're lustrous, so they're shiny. They're solid at room temperature with a high melting point and boiling point. Obviously, we have mercury as an exception. They're usually oxidized. They lose electrons during reactions. And they have low ionization energy and low electronegativity values. Non-metals, conversely, are poor conductors of electricity and heat. They can be a gas, they can be a liquid, they can be a solid at room temperature. Generally, they have lower melting points and boiling points. That does, of course, depend on the element. And they have high ionization energy and electronegativity values. The metalloids have properties which are intermediate between these metals and non-metals, and some are semiconductors. Trends in metallic character. Do note the trends in non-metal are just the opposite of this. Trends moving down a group. Metallic character increases as you go down a group. Metallic character decreases as you move across a period. Let's have a look at the examples. So potassium is more malleable than lithium. Okay, so you go down a group from lithium to potassium. Potassium is more malleable, it has a greater metallic quality. The melting point of barium is higher than that of magnesium, so you go down a group and the melting point is increasing. Nitrogen exists as a gas at 25 degrees, whilst antimony exists as a solid. So as you go down the group 15, you can see you've gone from a gas to a solid. And carbon, with the exception of graphite, doesn't conduct electricity, while tin does. So as we go down these groups, you can see that the elements begin to get the properties of metals, the properties that we associate with metals. Okay, let's have a look as you move across a period. The elements decrease in metallic character. Magnesium is malleable, but as you go along the group, you see silicon is brittle. You hit magnesium with a hammer, which has changed shape. If you hit silicon, it breaks. The melting point of calcium is far higher than bromine, so as you go along the group, the melting point is dropping substantially. Aluminium exists as a solid 25 degrees. Well, no, that's not a very good example. Just scratch it out. Aluminium exists at a solid 25 degrees, whereas chlorine is a gas. There we go. And copper is an electrical conductor, but selenium is not. That was quite a long presentation. Splendid. Goodbye.